Writing Lewis structures. This is a bit different way of doing it from what we did in Little Kid Chem. Suppose we have CH4. We still look up valence electrons. Carbon has 4. Hydrogen has 4 times 1H, 1 valence electron, so that is 8. We're just going to find out how many pairs of electrons there are available. 8 divided by 2 is 4. So you have 4 pairs of bonds. Carbon goes in the middle, 4 H's, 1, 2, 3, 4, all filled up. NH3, 5 plus 3 times 1, 8 divided by 2 is 4. N with 3 H's around it. 1, 2, 3. We always bond up all the atoms first. That's done. We got 3. We got 1 left over. So the middle atom needs another one. 8 is great. 2 is 2. Remember from back in the day. That's if you have extra pairs on the atom. HCN, 1 plus 4 plus 5. That's 10 divided by 2 is 5. C goes in the middle. N, H, 1, 2. Hydrogen's full up. 1, 2, 3, 4, 5. Times by 10. 1, 2, 3, 4, 5. Okay, I just can't count, that's all. So that's 5. Okay, so again, working on this, this is the way you do things with atoms. It goes a little bit quicker using the new method. If you have polyatomic ions, NH4 plus, 5 plus 4 times 1 minus 1, because if it's positive, remove 1, so that is 8 divided by 2 is 4. 1, 2, 3, 4, connect them. All 4 have used up. 8 is great. If it's a polyatomic ion, you put it in square brackets. SO4, 2 minus. Now let's do NO3, 1 minus. NO3, 1 minus. 5 plus 3 times 6 plus 1. If it's negative, you add it in. So that's 4 times 6 is 24 divided by 2, 12. N, 3 O's. First thing, connect them. 1, 2, 3. The outer atoms must have 8, always. So 1, 2, 3, 4, 5, 6, 7. Oh, that's what I did wrong. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Now if I put it here on the O, the N won't have enough. If I put it on the N, I need more, so that means you're going to have a double bond. Since it's polyatomic ion, slap a square brackets and a minus 1. There are exceptions to the 8 is great. Hydrogen is 2. Beryllium chloride beryllium has 2 valence electrons, plus fluorine, which is 7 times 2 is 14, 16 divided by 2 is 8. Beryllium is a very small atom. It can only hold 4 electrons for 2 pairs. So this one looks like that, where you have 8, but beryllium only has 2. Boron, another exception, it can have 6 electrons, or 3 pair. NO is an exception because 5 plus 6 is 11. You don't have an even number, so you can't really do that. So you're just going to match them up as much as you can. 1, 2, 3, 4, 5, and 1. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. That's 11. Maybe make it a double bond in there. Point is, you're going to have a singleton out there. That's very rare. Don't look at it very often. If we have XCF2, Xc is 8 plus F2. 14 is 22 divided by 2 is 11. Xe connects to the F's. Outsides must have the full octet. 1, 2, 3, 4. 1, 2, 3, 4. That's 8, 9, 10. Got one more. Xe is a big atom, so big atoms, it is possible to have more than that. And so that would be an exception. The only atoms that can have more than 8 are central atoms, sulfur, or bigger. Generally, it's better if you can do it with the 8 is great. If there's a chance of doing it, we're going to get more on which one is more likely to happen or not. Coming back up to here, let's not worry about the extra lines. On this atom, it's found out that there are not 2 single bond oxygens in one double bonded oxygen. It actually acts like 1 1/3 electron, or 1 1/3 bonds on all of them. One of these electron pairs is delocalized, which means it resonates or fills in all the gaps. It also makes it 120 degrees, which we can talk about bond angles later on. So this is an example of something called resonance. Don't worry about resonance unless somebody's on the test or quiz says, consider resonance, and then you do. The traditional way of showing resonance is to show all the possible permutations of where the double bond goes. A new wave, and then square brackets means it flip-flops all the way around. A new way of showing it is to show single bonds and then a dotted line. Now, you can't count the pairs on this like you do on the other ones, but it does represent that even more than the old style, that yes, we have more than a bond but less than a double bond going on. Formal charge. If there is a more than one way of writing a formula, you can predict This is not set in stone. It's just a tool. Which way you can think is more likely to do it. The formal charge, you calculate the relative charge, which is the valence electrons minus the, what I call marks. A lone pair counts as 2, a bonding pair counts as 1. One of the two electrons is with it all the time. You can look at it as a dot or a dash. If you can see it, you count it. So the valence electrons minus the marks. Up above here, we can have two possible formations of this, or variations. This isn't resonance. This is structurally the way it is. One, two, three, four. 1, 2, 3, 4. Or you can have another one would be a single bond and double bond. That's another permutation on that too. But we're going to go with the extreme here. Fluorine, there is a valence of 7, and there are 1, 2, 3, 4, 5, 6, 7. So 7 minus 7. There's another fluorine over here, exactly the same, so 7 minus 7. And the xenon, it has 8 valence electrons minus 1, 2, 3, 4, 5, 6, 7, 8. 8 minus 8. And the total charge on the thing is 0. If it was a polyatomic ion, like a -1 charge, you'd end up with a -1 total. Consider that with this. Fluorine has 7, fluorine has 7, xenon has 8. 1, 2, 3, 4, 5, 6, 7 minus 6. Same thing. And 10. This is 1, this is 1, and this is -2. Gives you 0. So you did the math right. Make sure you do it. Which one of these is more likely? Well, there's 2 rules. First one that gives you the most zeros wins, which obviously is here because they're all zeros. So this gives you the most likely form of xenon difluoride. If there was a tie, then you would get make sure that the most electronegative atom has a more negative charge, a more negative formal charge. Fluorine is the most electronegative, and anytime you see fluorine with a positive, you know it's wrong. 0 is better, -1's okay, 1 is bang. And noble gases are going to be 0, so that's bad on 2 different fronts. If you did another form of the same thing, I think 11. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. If we did this one, this is 7, 7, and 8. 1, 2, 3, 4, 5, 6, 7 on the left fluorine. This is 6 on the right beforehand, which is 1. And this is going to be 1, 2, 3, 4, 5, 6, 7, 8, 9, which is -1. Better than the other case, but this is obviously not the one that works. Formal charge, you don't do it every time, you don't do it any time except when you are asked to do it. It's just a check, and even then, there are exceptions to the rule. Again, models are iffy. Don't trust models. They're simplifications and help you to understand what we can do for the most part.